am going to present the topic that I told is electrodeposition of cobalt transient phosphorus on copper line on P-type silicon wafer. And my name is Dulal, and here is a graduate student and Professor Shin and in the chemical engineering department at Azure University. The application of cobalt transient phosphorus as barrier or capping layer for copper interconnection in microelectronic devices. Normally, before people use aluminum wire in outer large scale integration, but copper has some advantages like low resistance. So now there is an immense interest in copper wiring. But the problem of copper wiring is that copper is very reactive metal than aluminum, and it oxidizes very fast and it diffuses in the silicon oxide layer. And to prevent copper from diffusion and oxidation, barrier or capping layer has been proposed, and there are some many materials like metallic or dielectric materials have been proposed as a barrier or capping layer for copper interconnections. Among those layers, it was found that cobalt transient phosphorus has some better protective ability due to its amorphous type of structure. And this cobalt transient phosphorus layer so far before fabricated by electrolysis deposition, and that is without applying any current. And so far there is no report in the literature for electrodeposition of this layer. But there are some disadvantages like electrolysis deposition. First of all, it is very selective, and the phosphorus plays a very important role in stopping the grain boundary to protect copper from diffusion. But phosphorus content more than 10% is not possible by electrolysis deposition. And also for electrolysis deposition it is higher temperature. However, there are some advantages for electrodeposition. So our aim in this work is to electrochemical studies to see the possibility for the electrodeposition of this capping layer and electrodeposition and the characterization. The experimental condition, we use electrolytic cobalt sulfate as a source of cobalt, sodium tungstate, and sodium hypophosphite, and trisodium citrate as an complexing agent. 3 electrode cells we use. Normally people use 3 electrode cells for electrodeposition process or electroanalytical study. So we use copper disc electrode as a working electrode for electroanalytical study for the deposition of this cobalt transient phosphorus layers, and then we deposited the layer on copper coated silicon wafer to study the properties. And silver chloride or reference electrode and platinum coated. Now all the study was done at the room temperature, and we did not adjust the pH. It is a freestanding pH, and it was 6.9, very neutral pH. So this is our first experiment, very simple cyclic photonogram of cobalt sulfate solution in ionized water, and we started scanning from -0.1 volt to the more cathodic direction, and we got 4 point something here. We got a peak, and then when we proceed further, so it gives a peak over over here, which is due to the negative sign of the cobalt. And with further increase of potential, the current decrease, and eventually at here the hydrogen revolution from bulk solution started on reverse here. So at this point, the dissolution of cobalt from the electrode start. So this looks a very small peak, and this peak is not actually the reduction of cobalt. It is, of course, reduction of cobalt, but not the deposition of cobalt. It is a monolayer deposition of cobalt, which is called under potential deposition. And this curve is just the in larger resolution of this peak. And this is a cyclic Voltamogram of solution which contains both cobalt, tungsten, and phosphorus. And in this, so there is around at this potential the reduction of the species started, and we also got a limiting line over here. And so on reverse scan, the field deposit around this potential. It is more cathodic than the cobalt only solutions. So this is the linear sweep Voltamogram of cobalt only solutions and at different scan rates. And this is 10 millivolt per second, and we go up to 15 millivolt per second. And this study was done to see the diffusion control or the chemical kinetical control reaction or not. And the plot of the peak current density versus peak current density versus the square root of scan rate. Normally, it gives it the straight line. Then we can conclude that this deposition occurs under mass transfer control. And this is only cobalt only case. And this one is when we use both cobalt, tungsten, phosphorus, and disodium citrate as an additive. And also in this case, we have this type of peak citrate and increased scan rate. And we plot the peak current density versus square root of scan rate, and also it gives a linear relationship. And we can also conclude from here that in this case, also the diffusion, the mass transfer occurs under diffusion control. And this is the linear sweep Voltamogram of various electrodes containing just here cobalt only, and then cobalt plus disodium citrate, cobalt tungsten, cobalt phosphorus, and cobalt tungsten phosphorus. So only cobalt only we see the deposition started at this potential. But when we use the disodium citrate, so the deposition starts around here. That means it needs more energy to reduce the cobalt from citrate containing electrode. And that is because citrate is known to absorb from the electrode surface and block some active surface area for the reduction of cobalt. Anyway, but when we actually put some phosphorus, then we have again got some this limiting current P, and it becomes again in mass transfer control. This is the current transient of solution containing cobalt, cobalt isotope, cobalt tungsten, cobalt phosphorus, and cobalt tungsten phosphorus. Current transient is that we step the potential from open circuit potential to a potential where the deposition occurs. And this shows that when we got only cobalt, it takes relatively long time to double their charging. But when we got phosphorus in the solution, the double layer charging is rather quick. And based on this current transient study, there is two models for the nucleation mechanism in electrocrystallization proposed by Shorifkar and Hill, and we will show those model over here. So there are two types of nucleation. One is instantaneous, another is progressive. Instantaneous means at the beginning of the electrodeposition process, all the nucleus form once and grow gradually. But in progressive nucleation, the nucleus at the beginning of the electrodeposition, some nucleus form, but with the progress of electrodeposition, more nucleus forms. And this is two extreme cases, and we compare our experimental study with this theoretical instantaneous and progressive mode of nucleation, and we find when it is only cobalt, then it actually deviates from both instantaneous or progressive nucleation mode. But when we add trisodium citrate, it follows the progressive mode, and which is actually very good agreement in the literature. But when we put phosphorus or tungsten in the electrolyte, it perfectly follows the instantaneous nucleation mode. And it was in the literature that cobalt, even if follows either instantaneous or progressive, but AFM study actually showed that cobalt always form nucleus instantaneously. And well, those are the electroanalytical study, and then we deposited this field perhaps for the first time on copper-coated silicon wafer, and this is the composition analysis that we got. In the thing we got elemental cobalt, tungsten and phosphorus, and some oxide and hydroxide of tungsten and cobalt as well. And those oxide we have also, we don't show the figure here. We have some electron spectroscopy which shows that the oxide is on the surface, and we have a poster as well. So in there we explain the depth profile. Anyway, so oxygen is mainly on the surface, and the carbon mainly the metallic tungsten and cobalt. So this is the X-ray on this deposited film. This one the substrate, and we deposited copper. This substrate copper has a strong preferred orientation of 1-1, and this is related to titanium silicon. So this is the as deposited film, and we got some hexagonal cobalt over here, and some cobalt and tungsten compound with phosphorus, and after emanating at 300 degrees centigrade per 1 hour, those main thing is we got some more intermetallic compound, which actually formed due to the activation by heating. And also there is another interesting that this hexagonal cobalt transformed to cubic FCC cobalt after emanating. So this is the ACM and AFM data of two different samples. One is deposited by applied potential, and another is deposited by applied current. And this is the A1, A2 is the surface deposited by applied potential, deposited by applied current, and it shows that this surface is rougher than this one. So we also actually vary the concentration of cobalt, tungsten and phosphorus in the deposit by varying the concentration of this precursor in the electrodes. And it also shows that if we have a large amount of cobalt in the film, this crystal gets very bigger, and this becomes more metallic. But if we have a relatively low amount of, it is very low, but it is lower, 64% cobalt, and then we get actually amorphous type of film, and we normally desire for the cathode layer that this type of thing. And this is the effect of the constant ion concentration on the thickness and deposition. Okay, so here is our conclusion that we did the electrochemical study for the first time for the deposition of this capping layer by voltammetry and photometry. So we found that co-deposition of these three elements occurs from secret electrolyte containing cobalt sulfate, sodium tungstate, and sodium hydroxide occur by nucleation process under mass transfer control. The nucleation is instantaneous. So X-ray study shows those have elemental component plus oxide. ACM and AFM images show that the film have critical modular structure with good uniformity and dense coverage and very smooth surface alloy. The deposition current density and thickness increase with increasing cobalt and phosphate ion and hypophosphate ion concentration in the electrolyte. But in the increase of tungsten ion concentration, the result in the decrease of current density and thickness. So we can actually deposit some film by changing the electrolyte concentration with a large variation of the component. Like cobalt can be varied 64 to 83%, tungsten 0.5 to 24%, and phosphorus 6 to 20%. And X-ray diffraction that the film containing 20% phosphorus normally amorphous, and if the film contains less than 20% phosphorus, then it is normally crystalline. So surface increase with the cobalt content. Thank you.